Hello, everybody. Welcome for today's webinar. Today's topic is CAE Fatigue 2020. Here we're going to introduce the CAE Fatigue technology to everybody that is not familiar with this technology, and we will also go through what's new with this release itself. Thank you for your participation. And if you have any questions during the webinar itself, please type them in the Q&A panel, and we will try to address them. If it is something that needs to be discussed at the end, then we will reply to those questions at the end. And if you are facing any technical difficulties, like you're not able to hear us or anything, then please do type that in the chat window and select all panelists to let us know. And with this, I will give the conversation over to Neil, and he will get started.
Thank you very much, Bhumi, and thank you everyone for joining this morning's session or this evening's session, depending on which part of the world you're in. Really appreciate you taking the time to listen to this webinar. I'm going to, as Bhumi said, I'm going to introduce CAE Fatigue 2020, but this will be the first time we've talked about this technology inside of MSC Hexagon. So it's really exciting for us to tell you all about what we're doing and how this is going to improve what we can offer to you as our partners and as our customers. I'm going to give a little bit of background on myself and the company very briefly. I think many of you on the registered on this WebEx know me already, but I've been involved in this technology for a long time, many decades. And what I guess makes me and my company CAE Fatigue a little bit unique is we started in the frequency domain, but we don't see that as a limitation or a disadvantage. It gave us, we think, a big advantage in that it gave us a chance to do things a little differently. So, for example, although we started in the frequency domain, we also now feel confident working with a lot of other technologies like loads management, test design, and we've also now added a time domain durability capability into our software. So we're on the one hand quite specialized, but at the same time quite general. I guess the really big difference we think about what we do is we're really involved in technology advancement. That's what really gets us excited. What makes us get up in the morning out of bed is that we wake up, and all of us, Stuart Kerr's online as well today with me, and I think the developers, and we really enjoy pushing the boundaries of technology. So I'm going to tell you what we've been doing, what we've done, and then I'll give you a little bit of a taster of what we're doing into the future, which is, I think, also really exciting. The software itself is being released through MSC Hexagon this week on Friday. So for those of you that want to try the software, that, for example, have MSC One right now, you can immediately use the software. You'll need to get a new license file to do that from MSC, but if you contact your representative, I'm sure they'll make that possible for you. So let me talk initially then a little about us joining Hexagon and how that's changed the way we're doing business, and how CAE Fatigue Vibration, which CFV, which was our original product, has transformed into CAE Fatigue, or CF, it's been called now inside Hexagon, and what that means in terms of the technology. So we, as I said, we started in the frequency domain. So we started around 7 years ago, 6-7 years ago, with a very niche product in the frequency domain, which was trying to address limitations in that technology that existed at the time. Now, there are many vendors out there that have been operating for 30, 40 years that all started in the time domain. And, you know, sort of we're all familiar with who those are. And they developed their time domain fatigue. They then developed frequency domain fatigue. And what we did was we enhanced that frequency domain technology. And that really started our path from 2014 onwards, with our original frequency domain technology, which we called CAE Fatigue Vibration, or CFV for short. It had a very advanced frequency domain fatigue analysis capabilities, plus very advanced random response capabilities. We've now extended that technology into the time domain, so we have a full time domain fatigue solver, We also have extended it into loads management and loads cascading and surrogate load analysis. And so this really creates a set of test-based software. And we're continuing to develop this. I'll talk a little bit about that at the end of this webinar. So what makes us different? I guess the main thing is that traditional fatigue software will tell you if your part will fail. I think what we would claim is that our software will tell you if it will fail and then why it failed and how to fix it. Because we create and we provide a lot of additional data. Data is really important. We know this right now in respect of this terrible COVID crisis we're having. You know, it's one thing having mathematical models, but if you haven't got the data to back those models up, you're kind of floundering around in the dark. So we provide a lot of data, and this is in the form of the fatigue data, but also random response data. And we can extend that on to deal with advanced topics like collision detection. We can do loads cascading, something I'll talk briefly about later, vector load analysis, surrogate load calculations. And it gets us into the world of standardized loads, reliability, and test acceleration. So we feel that the technology we have is quite sophisticated in what it can do. And it fits into 4 technology areas. And for this, I will show you shortly, we have 3 software packagings that address these. So we have our traditional or our original frequency domain technology. We have the time domain technology that I've referred to. And then we have something called premium, which is a packaging which addresses large systems where you want to do things like loads cascading and test design. So I'm going to be talking about these in more detail as we go through this webinar. So before that, I'm going to cover very briefly a little bit of technical background. And I am going to cover it briefly, but if anyone wants more information on this, we have more than you could possibly want in terms of material. So anyone that wants a lot more data on the technical background, please contact us and we'll provide it. So first of all, we're doing structural dynamics or structural analysis, I should say, rather than structural dynamics in different domains. I'm going to talk a lot about the frequency domain. In the frequency domain, we create things called transfer functions. And so if I wanted to set this out in a flow like this, I would talk about creating the transfer functions with Nastran, providing the loads separately, and then calculating the responses by multiplying the transfer functions by the loads using either this equation for single input or this equation for multi-input, standard technology. And what I'm showing here, though, is that you can do this for static models, in which case the transfer function is a unit load, or you can remove that restriction and do it for dynamic models. So the nice thing about the frequency domain is it doesn't care if your model is static or dynamic. You can follow the same process and get good results. In the time domain, you have really 3 options that you can follow. And I'm talking about this because I'm going to show you later that we can offer the 3 time domain options and the frequency domain option in a kind of a consistent manner. So it's really neat and nice that you won't be confused by the different methods, because essentially we see them as the same with different starting points. So you can do a linear superposition using stresses you get from a static analysis in the solver, such as Nastran's solution 101, in which case you're then going to do linear superposition using this equation. Or if you have a dynamic case, you can do either direct stress recovery from the solver like Nastran using, say, solution 103 followed by 112, or you can do modal participation factor output from the solver and do the stress recovery separately from the solver, and it's a little bit more efficient. So we separate those 2 approaches where you get the solver to give you the stresses. We're calling that direct, and we refer to that as Sol 112, or rather time 112 in our approach, or where you're doing the modal stress recovery separately, and we call that time 103 in our approach. So there we have it, the 4 approaches, which we can label solution 111 from Nastran, but of course there are all other solvers will give you the same data. Solution 101 for linear static, solution 103 and 112 will give you either direct stress or separately created modal stress recovery. In the frequency domain, what makes this really neat is that the process is very simple. The response is simply the input multiplied by the transfer functions, the system properties. And our software is able to give you this data in a nice manner, which makes understanding the structural behavior a lot easier. So I'll talk a lot more about this later, because this is the basis of why the frequency domain gives us so many advantages. So just a little couple of comments about domain transformations. So I'm going to talk a lot about the time domain, and I'm going to talk about a lot about the frequency domain. And in the past, these have all been separated. What we're trying to do is say that you don't need to distinguish between these. They're really just different ways of specifying the same data. So, you know, whether you're starting from a time signal or a PSD or a sine sweep or even a shock response spectrum or individual sine waves applied separately or together, we are proposing that these are all the same types of load, and you can transform between them. So we're very much involved in saying, if you give me this time signal, I can give you this PSD and it will be equal. It will do the same thing. If you give me several time signals occurring together, I can give you back the frequency domain form of that, the PSDs, plus the cross PSDs in what we call a PSD matrix, and it will be equal. And this isn't debatable anymore. It's been proven, you know, subject to some certain assumptions, this works. Okay, and so we now know today that works. You can extend this on and say, what happens if you've got a sine sweep? Can that be related to a PSD? And with some restrictions, yes, that's true also. We can make equivalence between those. Even if you have a shock response spectrum and you want to know what the equivalent PSD is, we think there's a way to do that. So this is something this is our future work, one of our future work items, to provide a mechanism to back calculate the PSD from the shock response spectrum, subject to certain restrictions. So a very, very quick walk through the technical background. So now, and as I said, if anyone wants more details, we can provide all the background you want on those technologies. So I'm going to go through and talk about the specific packages that we are now proposing to deliver through MSC and Hexagon, and they're going to fall into three parts. We're going to supply a time-based package for doing time-based durability and fatigue calculations, a frequency package which will do our standard frequency domain calculations, what most people know us or are familiar with when they think of us, and then the premium package, which has a lot of advanced features for doing test design, full body calculations. Although you can do full body calculations with the frequency module and the time module, what this package gives us some additional features like spot weld, seam weld, advanced random, loads cascading, and some of the things I'll talk about later. So these are our three packages, and they will be supplied through MSC1, which is the standard method or preferred method of delivery through MSC Hexagon. If you can't use the software through MSC1, there is also a standalone version, which we call Apex Aligned, because as you'll see later, we're giving it the same environment and look and feel as Apex. And into the future, we'll also be offering exactly the same technology through a solver-linked mechanism. I mentioned the Apex Aligned concept. We are moving towards a process flow environment inside Apex. So in this current release that's coming out this week on Friday, we will have a beta version of this process flow for people to have a look at. It's kind of interesting. It takes us away a little bit from the way we used to work, using only control file mechanisms. In the future, we're going to offer also the process flow. Just as a little bit of a teaser, I'll show you that shortly. But just to give you also an idea of the way the software works, this is our typical interface, and I'm just going to show you the help system, because what I want to do is make sure that everyone, when they first turn the software on, they're able to get into using it reasonably easily. So we provided a lot of tools. This start page is the first thing. So when you go into the software, this will give you a kind of a single sheet overview of what's possible. Then also within the help system is a start page. I think the first time you turn the software on, you will get this start page. And what this will give you is a lot of short videos and other material which will help you to understand the way the software works. It's going to give you initially in the first section various introductions to the form of the software. So again, you can see that software layout in a video in the first in the first video there, overview of the software layout. There's an introduction to the user guide, perhaps the most important document we have. There's also an introduction to the utilities user guide, more specialist, but might be interesting. Quick reference guide gives you the basic details of how every operation works. We have a technical frequently asked questions guide that might be useful. A couple of videos on results output, either results in graphical form, and this gives you an overview of what's available there, and also what's in the log file where there is other kinds of output. So this first section is all about how the software works. The second section is going to give you some basic overviews of specific analysis types. So first of all, how to do a single input PSD calculation. Secondly, how to do a standard time to PSD. This is our loads conditioning toolkit. How to transform time data into frequency domain form. This is the next guide is going to give you an overview of that. And this here we're seeing different time histories of load being taken in. Our very advanced loads conditioning, automatic loads conditioning toolkit, which takes the raw data, transforms it into conditioned data, and then from that we're able to get the PSDs and PSD matrices. We have an introduction to a multiple input frequency domain example, and an introduction to time domain calculation. So whichever one you're starting with, this is the place to go to see how to set up. Then we go into more advanced applications. So this first one is how to do a base shake on a printed circuit board, and how to extract the various results quantities from that. So this is quite a nice advanced application of base shake. Here we see the displacement of the board. So if you want to do traditional Steinberg type fatigue calculations using the displacement of the board, we can give you that data in very advanced form. The second application is a collision detection example. We have, in fact, it covers both collision detection on a satellite part and also the same thing on an exhaust. So what we're doing here is applying random vibration, looking at the displacement of the parts, and then looking at the relative displacement between those parts to see if there's a chance that the two parts could collide. So this is a really nice technology. It'll tell you, if this is possible from a probabilistic sense. The third application is loads cascading. So this is loads cascading, first of all, to a battery on a trailer, and then secondly, to a headlamp in a car model. And by the way, all these models are available. So if you want to try them out, you're able to do that. And the last example is a surrogate load calculation on that headlamp. So that's just an overview of the help system. I mentioned the process flow. I'm only going to give a very brief overview of this, but this is a new way of setting up jobs. And a lot of our existing users are familiar with our control file view. This is going to be an alternate way to set up a job. And so it allows you to connect to the stress results coming from the solver, apply your material properties, apply your loading, then look at the various results forms, such as PSDs, fringe plots. All the normal results are going to be available through this process flow. And we're releasing this in a beta form with this software just so people can take a look and give us some feedback. We also have a load scheduler, which is included with the software. And this is going to be a nice way to create duty cycles and use them in a typical analysis. And just to be clear, we're not discarding our traditional control file editor. This is really what advanced users will typically use, and this will continue to be available to us. So let me go on and talk about some specific use cases of the software. So I've talked a little bit about the technical background. I've shown you the new form of the software. Let me go on and just go through a few typical use cases. Perhaps before I do that, though, I'll talk about the general case. In automotive, there are a lot of applications of this kind of technology. The same in aerospace. And if we go outside of automotive and aerospace, we have, a lot of other industries. And what I've done here, just to be clear, for each of these industries, I've tried to identify the level of applicability. So I've given them either 1 tick, 2 ticks, or 3 ticks, or in some cases across, telling us whether the software and the technology is directly applicable, partly applicable, only a little applicable, or not applicable at all. So, for example, to railway parts, it's very applicable. Power tools, the vibration of power tools, very applicable. Heavy equipment, then I'd say very, very applicable, but there are some caveats there. I mean, one of the things we deal with on heavy equipment is large welds. So that's something we have to look at and come up with better solutions for large gauge welds. So this is the sort of overview. Now let me go into some specifics. So let's go through the technology areas and then see how the technology applies in each case. I'm going to start off with time domain, which is a little bit back to front because we started off with frequency domain and we ended up in the very last thing we did was time domain, but I'm going to go through it in the reverse way. I'm going to show you the time domain solution and then go on and show the advanced frequency domain solution. So for time domain, we have 3 modes of working. And I'll show you in the software how this works later, but we have solution 101, which is the linear static superposition analysis. So this is where you take a solver run from Nastran or Abacus or any other solver and do linear superposition to get your stress time histories and then do the fatigue calculation. In the software, we're going to refer to that as time 101. For the case where you write the stresses directly with Nastran or another solver, we call that time 112 because it's created from a Sol 112 direct stress output. And the third type is solution 103 or time 103, where you do a modal run, write the modal stresses, you do a modal participation factor extraction using solution 112 and an SDISP. And we then, inside our software, will combine those to do the stress recovery. So all 3 of those procedures are fully available now in the latest software that we're releasing this week. But yeah, as I said, mustn't forget we have a base shake frequency domain, which is where we feel really comfortable. We have a complete solution for this. I don't feel there's anything missing or could be done into the future. And we also have the same thing for multiple inputs. The case where you have, in this case of this truck cab, 12 simultaneous loading channels, and we have procedures for switching that loading into the equivalent frequency domain, applying it in the frequency domain to the model, along with Nastran transfer function results or Abacus transfer function results, and then going on to do the fatigue calculation. So this is also a very sophisticated and complete solution as far as we're concerned. Now, I said we have this consistent analysis flow, and I want to just show this to you. All of these test cases are available through the software, through the user guide, so all of these can be accessed. What we have here, and you're going to see the very latest version of the software environment here. So this is a really good overview of how the software looks today. Let me just get rid of that. So what we're seeing here is a model and various results forms, but I'm going to go back and start at the beginning. So I've got, you see, 7 analysis runs here, and I'm going to go through each one and show you the differences. The first one is the loads conditioning. Second is the frequency domain run. Third is an equivalent time domain run using solution 101, but with a sine von Mises output. The fourth is solution 101 time linear static with critical plane output. And then the last 2 are solution time 103 and time 112. Now, what's different about these, as I click through them, what I want you to see is that the control file is almost identical. The only thing that changes between these control files is the OP2 file that we read, and down at the bottom you'll see in a short while we change the type from PSD to time 101 to time 103 to time 112. So let me go back and look at each one then. So this is the first one, which does the conversion of the data from time domain to frequency domain. All this does is it transforms the time data which we have into equivalent frequency domain form over here. That means I now have 2 alternate starting points for my analysis. I can start from the time data, or I can start from the frequency domain data. Okay, now I'm going to go and do a frequency domain analysis with those PSDs. And in this case, I'm going to do the whole analysis. I'm going to look at the results by clicking on the results button. I'm going to look at the fringe plot for the stresses in this case, but I can also look at damage. I can look at many other results outputs. I don't have time here, but there are many other things. When I click on the max stress, I have to go to an event to see that. So you see I have the 7 different event results. I also have the event plot on the right there and the PSD plot at the bottom. So that's all coming from a frequency domain PSD type calculation. Now, when I go to the time domain analysis, everything looks the same, except I changed my OP2 file to be a solution 101. I have exactly the same results types. I can go to my fringe plot and I can change that result type to RMS, and I will get more or less the same stress. So what's the point here? Is that I can start from the same loading either in the time domain or the frequency domain, and I can get the same answer within certain bounds, whether I work in the time domain or the frequency domain. I can do a critical plane calculation instead of a sine von Mises calculation and get similar results. So what these test cases give you, and you see they have numbers 350 to 357, is the ability to look at all these procedures in parallel and see how they work and how the results change. And so for anyone wanting to get into this technology, I would recommend this is a really good starting point for looking at the software. Look at these test cases and you're going to get a good perspective. So let's go into the large multi-input frequency domain analysis and just look at that in a little bit more detail, because this is a really important application. This is where we're, really perhaps the most sophisticated thing we can do. Large numbers of channels, in this case, perhaps up to 90, large numbers of events, up to say 70 or 80, sometimes different weight conditions. So let's see the way that CAE Fatigue will do this. And for most of these applications I'm about to look at, there are SAE papers that we publish with customers, with partners on this. So this is, oh, by the way, I have to apologize. This video is using the old version of the software, so you'll see a slightly different color format here. The fringe plots and other things are going to look very similar. So here I'm looking at the stress initially, and now I've changed that to damage. And because damage is very localized, I've had to change the legend scale so I can see where the damage is occurring. So I'm seeing a couple of different red spots if I look carefully here, but there'll be multiple zones for these red spots, multiple hot spots. I'm going to talk about that a bit more in a short while. So here we're interested in where these damages are, but we might be interested in other things. But one thing might be the acceleration response of the car when it's running on different events. So here I'm showing the Z acceleration response for different events. I'm going to start off with event 1, and then I'm going to go through and look at what happens as we drive this car over different proving ground tracks. So first of all, event 101, and then as I go through each event, I'm seeing different acceleration response, which is really interesting. Now remember, this is just the Z direction. We'll have something similar for the X and the Y directions, and they may or may not be important to us. So these are all of the different acceleration responses. We can also go back and change that response to displacement and then ask for the relative displacement response. That's what I'm about to do now. So I change that to minimum clearance. Now that's going to show me the relative displacement between the car doors and the frame. And it's going to tell me under different loading scenarios, different events, how much of that clearance got used up by my loading in a probabilistic sense, because I'm doing a frequency domain run here. So I'm going to probably assign a 3 sigma, 3 times the RMS probability, and then say, based on that probability, did I lose my gap? Did my gap disappear? I can also go and look at things like other advanced responses, like the frequency at the peak response. So if I look at my PSD response and see where the most dominant mode was, and then I plot that frequency, I get this thing called frequency at peak response. Now, this is also a really, really interesting statistic, because this is showing me which modes are dominating the response for different events of the car. A really, really interesting statistic. Okay. Now, finally, I can go back and look at other, I mean, and by the way, all of these responses were created simultaneously on the vehicle. I didn't do 2 runs for these. I did 1 run, and I did the fatigue and stress, and then I did the random response. And now here I'm looking at the spot weld results. It's still got the frequent peak response. So let me go back and change that to, they say, stress. So if I change it to stress for event 1, so now this is the stress. Now I'm seeing a couple of high stresses, but if I change my legend scale, I'm going to get an idea of where things are really happening. If I change that to 20 megapascals, I'll see all the spot welds where I've got stresses above 20 megapascals. And stress may be interesting, but I may be more interested in damage. So if I go and put damage there and then change my scale again to give a realistic maximum for the damage, I'm going to see those locations where I have an issue, where I need to think about doing something differently. So all of those were outputs from a single run, and there are SAE papers which we can share with you, which will explain that. Something which we also do, and it's also a test problem that can be provided to you if anyone wants it. Something we do as part of that run, if needed, is provide the ability to reduce the output based on the hotspots. This is a plot of the hotspot stress with layers kept around each one. So here we have 300 hotspots with 12 layers surrounded around each one. So let me go on and look at other use cases. I've referred several times to the load conditioning. We have a lot of material on this, including SAE papers, which we can share, which explain how this conditioning is done, how the data is stored, how it then gets used in the follow-on analysis. So this is something that we will, we feel very proud about this technology. It has various automated procedures for removing unnecessary parts of the data, for doing the Fourier transformation in the correct manner. And we continue to work on this, but we already feel this is a very advanced capability. So let me talk about some other specific applications. Mixed loading is a very important topic for us. We're able to mix PSDs with sign sweeps, with simultaneous signs, with consecutive signs. And again, we have a lot of material on this, and including SAE papers, which we can share. The topic of loads management is important to us. So we have a lot of tools for mixing loads and for managing loads. And into the future, this should really be in the future work area, because we feel that what we're aiming for in the future is a unified loads management toolkit. So we would like to say in the future, it shouldn't matter where your loads come from. We should be able to give you a mechanism to handle those loads in either domain, time, or frequency, depending on what you want to do. So this is really my roadmap for the future of loads management. But it's what I'm going to focus on just in these next couple of slides is it's a bit more how we would do it for a typical car body, how we would do loads management for a car body. So here we have a car where the road surface profile is coming into the car. So this is what I'm trying to show here with this series of ones, the road surface profile. How would we normally do this? Well, we have a couple of options. One is we might feed that road surface profile into a multi-body dynamics code like Adams. We might then feed that up through the suspension system with Adams and create body loads on the vehicle, which would become the input to our part of this process. So that's typically how we would get the body loads, either from multi-body dynamics totally, or from multi-body dynamics with a little bit of a measurement of the wheels force transducer loads. So what we can do with this is take those time domain loading files and do body durability with our time domain tool. That's certainly one thing we can do. Or we could take our conditioning toolkit and turn the body loads into the frequency domain, and then do body durability in the frequency domain. And obviously, comparing these two is important. They should be similar, which we can show through SAE papers. We do get similar results for these. Okay, but we can go beyond this. We can say, what happens if we also ask for the displacement on this car vehicle? I showed you earlier the ability to do a collision detection or rattle. That's an ability that comes from this advanced random analysis procedure that I've been showing. We can also ask for component loads. So we can say, what happens if I push my loads up to the battery compartment and represent them at that location, and then reuse them at that location? So that's what we call loads cascading. And then what happens if we take those loads and simplify them? That's what we call surrogate loads analysis. And all of these steps, or at least steps 4, 5, and 6, and 7, are test problems that we can share with you if you're interested in seeing how this works. This isn't something in the future. This is today. This is what we can do today with the technology we have. Okay, part of that, I talked about random response collision detection. This is a very big topic. I don't have time here to go into details, but I can share with anyone that wants it much more details on this. But this is a very sophisticated capability for doing both random analysis and relative random with collision detection on various parts. It's being used by many of our customers to see if things will interact with each other during the operation of the vehicle. So loads cascading I referred to there. Again, this is the ability to take loads at one point in a vehicle, push them through the system to subframes or components, and then reuse them at that location. We can do this with accelerations. So let's say take the car example where the loads start off as forces. We can start with these forces and push them up and represent them as acceleration PSD matrices. That might not be ideal for situations where you have load application points which are separated in space. So we can also do this for forces. So we can take the forces coming into the vehicle and represent them as component loads, but in the form of force PSD matrices. So this is something we are able to do today. And some of our partners and customers have been doing this kind of work. So we have an SAE paper which shows this being done for loads cascading up to a seat model in a vehicle here. We also have another SAE paper showing similar technology being used for the prediction of what we call cutting plane loads. So this is a situation where you would have a measurement of responses on an in-service part, like an exhaust. You want to take that exhaust back into the laboratory and apply loads to certain parts of it. And what our software will do is give you the cutting plane loads, so that if you extract parts of this assembly and want to test it, we'll tell you what the load should be on those boundaries, on those interfaces. And it is a paper that can be shared if anyone's interested in seeing how that works. Our most recent technology development is in the area of test design. And so there is a capability in our software for applying a vector load onto a part and then finding the best direction for that vector to give the optimum correlation with the original requirements for the damage on that part. So this has been published in a paper. There's a specific SAE paper published this year which shows the process. And we also have a test problem in our test problem library which will go through this process. It's a very advanced topic, but it's something that we think can be further developed and enhanced, and it's an active area for us going forward. So test simplification and test acceleration is definitely a big part of our future work. We have technology which I talked about, vector load. That's part of a more general capability called surrogate loading, where we can take complicated loads like this and calculate what their equivalent would be in simplified form that will do the same thing, but can somehow have the same influence on a part or an assembly. So this is, again, a part of our software. It has, there's an SAE paper or several SAE papers which, and NAFEMS papers which talk about this technology. We've also done it for slightly more complicated scenarios. So this is a paper that was published recently showing how to take complicated loading on an axle part and then represent that loading as single sine wave inputs onto the various channels, but phased and with certain amplitudes such that the combination of those gives a similar damage distribution on this axle. Why would you do this, by the way? That's an interesting question. Well, To apply these loads to this axle requires a multi-million-pound test rig that very few OEMs, well, most of the OEMs have, but very few subcontractors would have. Applying sine waves can be done with simple actuators. So this is a really nice way to simplify design and then share that design with subcontractors to create, if you like, standardized loads. We've also done work on loads tuning. So this is an interesting concept where you have measurements from the track, you have measurements and responses in the laboratory, you have the CAE version of these, and using these three together to make sure the laboratory testing does what you think it did is what we call loads tuning. And it's an active area for us going forward. So I've talked a lot about things we've done recently. I want to just spend a few minutes talking about the future. Let's take a quick look into the future, because for us, this is, you know, what as I said, what gets us up in the morning. My big idea is, or it's not my big idea, but the big idea is when you're working in the frequency domain, the relationship between the response, and the inputs and the structural system is very simple. You take the structural system, you multiply it by the loads, and you get the response. This is what I call a fully defined system. Now, what we know is if we know two of these, like if we know the inputs and the transfer functions, we can calculate the response. This is the way our software typically works. Most of the examples I showed you earlier today showed exactly this case. Make an Astran model, make an Abacus model, put loads onto it, and we'll get the response with those two. But what isn't always obvious is that there are different ways of doing this. So what happens if you've got the response and you have the inputs, but you want to know what the structural system is? This is what happens if you take a part, or even a full vehicle, like a car, hang it off ropes in the laboratory, hit it with a hammer, and then measure the responses. You know when you hit it with the hammer that you put white noise into it. If you measure the responses, what you end up getting is the transfer functions when you measure the data there. This is commonly done in the laboratory, and we can do this in a software environment. We don't have to do it experimentally. We can do it in the software environment. And this can be extended to this case. What if you've got the response and you can develop the system with Nastran or Abacus, and you want to know instead what the loading is that would cause that? This is our surrogate loads concept. So we can calculate the loads once we know a target response. That's what we've been doing with various papers recently, which we can share with you. And this can be extended even further. What happens if you have your structural system with Nastran or Abacus and you have an acceleration response? What can you do with that? Well, in this case, we can say, well, what were our loads? Go back to the loads from the response in the transfer function. Now we know the loads. Let's go back up through our system and calculate the fatigue response. You can think of this as a fatigue map concept. And this, I think, will be a huge topic in the future and something we're actively working on. So one thing for the future I would like to think about is what happens if we put accelerometers in a car, we measure those, and we use, with our software, we use those accelerometers to back calculate what the loads are, either at the wheel or more likely at the body load position from these measurements. I'm calling this virtual remote parameter control because it looks very similar to what you do with remote parameter control when you take remote measurements like strains back into the lab, use an RPC test rig, and then calculate the drive files for that. So what I'm proposing here is a software version of this, a virtual remote parameter control, where this could be done either as a post-processing operation, or why not think about doing it real time? So measure these loads as you're driving along and calculate real time what the body loads are, and then calculate the fatigue response real time during the same process. So that's the most complicated scenario. We can go to something a little simpler. This is a bracket which has the potential to have a measured response here, say, or here. And what our software will do today is calculate for you the loading that causes that response. So although I've got this in the future work section, it's actually what we can do today with our software. This is something we're very, very interested in. So I've given you an overview of the software, some use cases, some pointers to the future. There are many technical papers which we have. I have 3 slides here explaining which these are. If anyone contacts me, I can point you in the right direction to get hold of these. Some of them I can share with you. Some of my old PhD thesis, some of these old papers can be shared. Others I'll give you the reference for SAE or NAFEMS, and you can get them from those. This is the papers up to April 2006. This is what we published in, well, I say we, a lot of times these were done with our customers and with our partners from 2016 to 2019. And you'll see just this last year, in 2020, in fact, in this last year, we've published, I think, nearly 10 papers. So we're very much about technology advancement, and we want to work with customers. If you come to us and say, we have this challenge, help us do it, we'll certainly do it with you. The contacts, if you want to get hold of myself, I'm Neil Bishop here, and my colleague is also someone that you should have the details of, stuart.kerr@hexagon.com. And I want to just say one last thing. The software itself is being released on Friday in 2 days. And if you're an existing MSC user, you'll probably need, and probably you will need, a new license file. So you should get hold of your MSC contact and just say, give them a nudge, tell them to get that organized, because I guess it might take a couple of days to get. So with that, I'm going to pass it back to the host, Bhumi, and see if we have any questions, anything that we want to talk over in more detail.